Hello. In this video we're going to explore in more detail the idea of the relativity of simultaneity, and then we're going to learn about one of the most important ideas in special relativity, the space-time interval. Let's suppose that we have two observers, S and S prime. S sees two events, and those events are at locations x1 and x2. And so they say the separation in space, so the spatial distance between those two events, let's call that delta x, is simply the difference in those positions, so x2 minus x1. Similarly, they measure the time of those two events, t1 and t2, and they say the time interval between those two events, so how far apart they are in time, is given by delta t equal to t2 minus t1. An observer in S prime, so this is another frame of reference moving at speed u relative to S, they also see those two events. And similarly, they measure their locations, let's call that x1 prime and x2 prime, and their times, t1 prime and t2 prime. And again, they will measure delta t prime, which is t2 prime minus t1 prime, and the spatial separation, delta x prime, x2 prime minus x1 prime. Now, with a little bit of substitution, we can see that the way that the intervals, delta x and delta t, transform is very similar to the way that x and t transform. So what we'll have is that delta x prime is given by gamma into delta x minus u delta t, and delta t prime is given by gamma into delta t minus u delta x over c squared. So really exactly the same as the Lorentz transformations, but now we have these deltas in there. And in fact, if you think about it, the original Lorentz transformations that we wrote down are really just a special case where the interval is between the position x or t and the origin 0. Now let's suppose that observer S says the two events are simultaneous. So that's the same as saying that t1 is equal to t2, or that delta t, the difference between t1 and t2, is 0. So what does the observer in S prime say? Well, the observer in S prime says that delta t prime is given by gamma into delta t minus u delta x over c squared. Well, delta t is 0, so that's just minus gamma u delta x over c squared. So as long as S prime is moving, u is not equal to 0. And as long as S didn't say the two events were at the same place, that means that delta t prime, the separation in time as measured by S prime, is not equal to 0. So delta t prime is not equal to 0, and so it's not equal to delta t. So what we're saying then is that two events, observer S says they are simultaneous, but not at the same place in space. S prime will not say they're simultaneous. They say they happen at different times. And of course, this is exactly what we saw in the ladder in a barn paradox, because the farmer's wife, who was sitting on the ladder, did not agree with the farmer that the two doors were closed simultaneously. So we might wonder, well, if S and S prime don't agree on x and t and delta t, is there anything they do agree on? Well, one thing, of course, they do agree on is the speed of light. That was the ingredient that went into special relativity, and that's where we get all this from. But it turns out there are other things they agree on as well. A quantity that does not change between frames of reference is called a Lorentz invariant, i.e. it doesn't change, it doesn't vary when we make a Lorentz transformation. One very important Lorentz invariant is called the space-time interval. So the space-time interval is defined like this. We say that delta s squared is given by c delta t squared minus delta x squared. So what we're talking about here is two events. They are separated in space by some distance delta x, and they are separated in time by some distance in time, some interval of time delta t. And then we can calculate this thing called the space-time interval, which is the time interval squared multiplied by c squared, and we subtract the space interval delta x squared. And this space-time interval, delta s squared, is the same for all observers. So a different observer will look at those two events, they will measure a different delta t and a different delta x, but when we combine the delta t and the delta x in this way, we will get the same delta s squared. And you can show that by substituting in the Lorentz transformations into this equation. This is particularly interesting because the sign of delta s squared tells us something important about those two events. Let's suppose first that we calculated delta s squared for a particular pair of events, And we found that this was less than 0. And of course it can be less than 0, that just means that this second term is larger than this first term. This is why we tend not to talk about what delta S is, because then we might need to take the square root of a negative number, so instead we're going to talk about delta S squared. Now in this case, if delta S squared is less than 0, as we said, that means that delta x squared is bigger than c delta t squared. And so delta x is bigger than c delta t, where we're assuming that these things are positive, so we can put in our absolute signs there. Now what is c delta t? C is the speed of light, delta t is the time interval between the two events. So c delta t, that's a distance, and in fact it's the distance light could have travelled in the time interval between the two events. So what we're saying here is that the events are separated by a distance which is larger than light could have travelled in the time between the two events. We call this space-like separation. What it means is there's no way one of those events could have caused the other event. There can be no causal link between them, because the fastest anything can travel is the speed of light, and even light couldn't have got from one event to the other in time. The other case is then delta S squared is larger than 0, in which case delta x is less than c delta t. We call this time-like separation. In this case, light could have travelled between the two events. We can also define the intermediate boundary case where delta S squared is equal to 0. We call this light-like, or sometimes null. And we can just really think of this as being the boundary between these two other cases. So the separation between the two events in space was exactly right, so that light could just have got from one event to the other event in the time interval between the two events. And remember, everyone agrees on delta S squared. So everyone agrees on whether delta S squared is positive or negative. So everyone agrees on whether those two events were space-like or time-like or light-like separated. So it can never be the case that two different observers disagree on whether two events could be causally linked or not. Everyone agrees on causality. And in particular, what we find is that for time-like separated events, everyone has to agree on the order of the events. Whereas for space-like separated events, which cannot be causally linked, they don't necessarily have to agree on the order of the events. For time-like separated events, there can be no observer that sees both events happening simultaneously. That's because c delta t has to be bigger than delta x. Well, the smallest this can be is 0, so this has to be larger than 0, so delta t has to be larger than 0, so there has to be some time separation between them. Similarly, if they're space-like separated, then we can never see those two events happening at the same point in space, because delta x is always larger than c delta t. Even if delta t was equal to 0, delta x would still have to be larger than 0. So we're really starting to get used to the idea that we can't really think of space and time as being separate things. We think of them now as two coordinates within this larger thing that we call space-time. A space-time diagram is a way of illustrating how objects move around through space-time. Now, space-time is four-dimensional. We have x, y, z, and t. It's very hard to draw four-dimensional diagrams. So what we usually do is we draw two-dimensional diagrams. We show one of the spatial coordinates, usually x, and we show the time coordinate. The x coordinate goes along the x-axis, and then the time coordinate goes along the y-axis. And we don't actually plot t, we plot ct, speed of light times t, so that this coordinate is also a spatial distance as well. And then let's suppose we have some object, some person, and they are sitting in a place and not moving. So their world line, their trajectory through this space-time, is going to be a vertical line. They're not moving in space, but they are moving in time. If they were moving in space, then now we'd have an angled line, such as this. So now they're moving in both space and time. Now imagine we had something moving at the speed of light, so light. Well, the world line for light would look like this. It would be a line at 45 degrees, providing we've chosen the same scale for the two axes. Now nothing can travel faster than the speed of light, which means that the world lines for any other objects must always lie at a shallower angle than this 45-degree line for light. In fact, we talk about the idea of a light cone. So this is the area of space in which it is possible for the world line of this object to go. And similarly, we can draw it backwards. We can see where the world line has come from, where this object could have come from in space-time. There is no way for the object to communicate with events outside of this light cone. So for example, a space-like separated event, so space-like separated relative to the origin in this case, will lie outside of this light cone, whereas a time-like separated event will lie inside of the light cone. Now, of course, we've drawn this space-time diagram from the point of view of a certain frame of reference. We could draw this now from another point of view, another frame of reference, and then the space-time diagram will be different. There are ways of drawing multiple frames of reference on the same space-time diagram. You have to add in additional axes. And it turns out the way to do this is actually to tilt the axes relative to the other frame of reference. We're not going to go more into that here, but there's a link in the description if you'd like to read more about that. So now suppose we have two events, event 1 and event 2. We will draw these on a space-time diagram from a particular frame of reference, let's call it S. They are separated in time, but we're going to say that they happen at the same point in space. And then we could calculate the space-time interval, the space-time distance between those two events, delta S squared. Now let's think about the point of view of another frame of reference, S prime. We can draw a space-time diagram from their point of view. This second observer is not going to agree that those two events happened at the same point in space, because this observer is moving, and so in between the two events happening, the observer is moving, and they say the relative location of those two events to them has changed. So it might look something like this. So now we have some spatial separation and some time separation. And the total separation, the space-time interval, is as shown. Now if you look at these diagrams, you might say, hang on, for S prime, that space-time interval looks bigger. And haven't we just said that everyone agrees on the space-time interval? If the horizontal and vertical separations between these two events in this diagram were spatial differences, then the total difference would be given by Pythagoras' theorem. We'd square both those distances, sum them, and then take the square root. But that's not what we do for the space-time interval. The space-time interval has a minus sign in it. So in a sense, this spatial separation makes a negative contribution to the space-time interval. And so when we go and calculate the space-time interval, we will in fact get the same value for these two cases. So this is showing us that space-time really has a different geometry to space. And it's that different geometry that really makes special relativity so hard to grasp, because it's really not the kind of geometry that we're used to thinking about. We could spend lots of time talking about the space-time interval and how to draw different situations on space-time diagrams. There's lots of resources out there if you want to look more into that. In the next video, we're instead going to move our attention to something called the relativistic Doppler effect. Please don't forget to subscribe, and I'll see you again soon.